Welcome to this video about the magnetic field that will will be shown when you have a single circular wire or a coil. Now, in order to understand what is going on, we first have to quickly recap what happened in our previous chapter when we were studying the magnetic field and the field vectors for conductors, and we started off with a straight wire. Now, for a straight wire, your field lines were always concentric circles with the actual conductor as its center. And if you knew that this was the shape, all you had to do was determine the sense of these field vectors, and you had to use the first right-hand rule. The first right-hand rule said that you had to use your thumb of your right hand to follow your current I, in this case, and then your four fingers would indicate what direction the field lines would be turning, meaning your field vector on the left-hand side here would be coming out of the page, while your field vector on the right of the straight conductor would be going into the page. And we introduced these two new symbols to indicate the arrows for these situations. Now, let's look at what this teaches us when we look at, in this case, scroll a bit, a circular wire, which is the new subject of today. Technically, when you have a conductor that is twisted into a single circle, your current is always going to flow in one direction. In this case, counterclockwise, going this way around. You can use your first right-hand rule on random intervals on this circular wire. If you do so, you follow the current I with your thumb, and then you look at the four fingers to indicate how the field lines would be turning in this case. So imagine that we get our concentric circles again. They would be turning this way, meaning the field vector will be coming out of the page on this spot, perpendicular to the page but pointed towards you, and perpendicular but pointed away from you outside of your ring, outside of your circular wire. And you can do that for all the remaining spots. Technically, you could draw the same thing here, like so, and you could draw the same thing here, like so. Following our right-hand rule, we know that this is the sense of all of the field lines. And we know if we took the tangent lines, we can determine our field vector B in these situations. And doing so shows us that all of the senses inside of the ring are identical. They're perpendicular, but pointed outside, or towards you, sorry. And these are perpendicular and pointed away from you, outside of your ring. Meaning you can simplify this situation to this. Your field lines are all perpendicular in the center towards you and perpendicular away from you outside of the ring, which leads us to the second right-hand rule. If you take your hand and you assume the same position as the first right-hand rule, but you now use your four fingers to follow the current along, your thumb will indicate the sense of the field lines in the center of your ring. Meaning, and we can fill this in, follow the current I with your four fingers, meaning clockwise or counterclockwise. And your stretched out thumb will indicate the sense of the magnetic field vector inside of the circular wire. For the outside, of course, it will be the opposite sense in this case. Now, we've always been looking at this from a frontal point of view on our ring. You can also look at it from the side. And in order to understand, I think situation C is actually the best type of representation. Situation C is just the same one as this, however, looked at from the side in this case. Now, if you take your four fingers, they would have to leave your current out of the paper towards you on the top and going into the piece of paper at the bottom here. If you do so, and you follow that along, coming out of the page at the top and into the bottom, your thumb is pointed towards the right, meaning your magnetic field vector is going from the center to the outside, like this. Essentially, situation C is the exact same situation as situation A, where they use the same indication of your current, coming out of the page at the top here, going into the page at the bottom, in this case. If you follow that along, you will notice that your field vector B is pointing, again, from left to right. If we draw the field lines from this circle, and we add this more completely, you will notice that this is essentially a very flat type of bar magnet. A bar magnet consisting of a very thin little bar, with the field lines going away from the virtual North Pole and coming towards the virtual South Pole. In essence, this circular ring behaves like North Pole on one side and South Pole on the other. And this is with the current going like this, in this situation, coming out of the page at the top and into the bottom. Should you turn the current in the other direction, should you switch the polarity, of course, the polarity of your magnet will also change in this situation. Now, how strong is this field vector? For a circular wire, we will not be looking into this any closer, but we will do so for a coil. Now, what is a coil? In essence, a coil is often wrapped around a central substance to increase the potency of the magnetic field. So in other words, the bar in the center here will most likely be a ferromagnetic metal. Why ferromagnetic? Well, we will learn that this will increase the strength of this magnetic field. Now, if you use this as an electromagnet, you will actually have to run current through it. And you will notice that because of its shape of the coil, this actually behaves very similarly to a bar magnet in this case. Now, in order to make this more clear, I've drawn the situation of this bar magnet, however, without the metal, ferromagnetic metal bar in the center. In this situation, you have the two poles of your voltage source. Current will start flowing like this, follows the full lines, goes downwards on the dotted lines, but we won't draw these, and will come out again. Now, I know this isn't the perfect spiral, I just drew this in MS Paint, so it's not exactly very three-dimensional, but as you can see, this is the indication of the sort of the turning sense of your field lines. Now, if I use my right hand rule, it means that my four fingers have to be coming out of the page here at the bottom and turning into the page here at the top. If I wanted to do that, and if I followed the current along, it would mean that remember, for the right hand rule, you have to look at your fingernails, because we always draw the turning sense on the full line, never on the dotted line. My thumb is pointed towards the right. So this would be the direction of your thumb in this case. Now, what does that mean? That means that this side would be the virtual north pole of my bar magnet, the side indicated by the thumb, and this would be the virtual south pole. What does that teach us? Well, our field lines are going to be the same shape as a bar magnet. Normally, when you draw a bar magnet, you start off with the central line like this. But in this case, you can actually sort of elongate it and draw it all the way through. The next few lines you had to draw started at the top here, right, and went in one direction like this. Next field line you draw is slightly closer inwards and then turns like this. And then the further you go inside, the harder it becomes to still connect these two. This is sort of the shape that you get. I was a bit too enthusiastic with this one. I hope I can still erase this one. Oh, there we go. Like this. Now, the hardest part of this is doing it nice and symmetrical on the other side. So this would be the field that is created below the magnet, exactly as we saw with our bar magnet. Now, what will be the sense of these field lines? We've learned that the field lines are going away from the, in this case, virtual North Pole, and will be aimed towards the South Pole, as you can see. This kind of creates a double situation. On the outside of your coil, you have the exact same field as you would get with a bar magnet, but on the inside of the field, something interesting happens. You get a homogeneous field. This homogeneous field on the inside of that coil is the one we will be studying further when it comes to determining its strength. Now, in order not to make the video last too long, I'm going to pause it here and just write down the second right-hand rule, and that one says, for a coil, follow the current I in this case with your 4 fingers. Your thumb will indicate which side of the coil will act as the North Pole for determining the sense of the field lines. So you use the second right-hand rule to determine the sense of the field lines of your coil. And essentially, this situation combines what we've learned previously with our bar magnet in this case. I will see you in the next video to talk about the strength of this magnetic field a bit more. See you then.